Hello friends, welcome to our channel. Let's look at problem 1928, minimum cost to reach destination in time. So in this video, we're going to use Dijkstra's algorithm. Dijkstra's algorithm. So here actually this problem is different from the previous one on previous video in which we use Dijkstra's algorithm. So here actually we need to visit all the cities, but we have to consider two factors. First is the time. So we have a time constraint. So we need to arrive at the city n-1 within, that is less than or equal to the maximum time given. So this is the one thing. And we want to find the minimum cost. So here the cost is computed by the summation of the passing fees, right? For example, if you in example 1, if you want to from house 0 to house 5, so if you take the path from 0 to 1 to 2 and to 3, so the time in total is 10 plus 10 plus 10, that is 30. But the passing fees is 5 plus 1 plus 2 plus 3. That is say 5 plus 1 plus 2 plus 3, 11, right? So that's the output, right? So we need to do all this Dijkstra's algorithm as before, but here we have two, we can interpret the time and the cost as two different distances. So here we have two distances. So here I'm using quotation marks because if I see the passing fees and times distances, it's not very rigorous, but this will help you understand. So here this problem is marked as hard. So actually from algorithm level it's not new, but for newcomers maybe you need to know Dijkstra's algorithm first, and then you add the tunes for the two distances, then you are going to finish the task. I guess that's the difficult part. But if you are very familiar with Dijkstra's algorithm, and then though we have the time constraint, so you should still be able to do this. So let me recall some information, right? So in Dijkstra's algorithm, so basically if I'm typically implemented using min heap. That's the one ingredient. Another ingredient is relaxation. Relaxation. So basically, if, for example, from the source to a node, you have a cost or distance, that is du, and then so to v you have a dv, and then there have a distance or cost from u to v, right? So then if I from the source to arrive u, and then from u arrive v, by, in other words, arriving at v by v of u. So if du plus duv is less than dv, therefore we are going to update this to be this guy, right? In other words, we find a shorter path by v of u to arriving at v. And then also, if you want to have a previous, retrieve the previous nodes, you are going to set the previous of v is u. So this is the relaxation. But here in our solution, so we are going to use Dijkstra's algorithm. This is for sure. And the case thing is demonstrate to you how to incorporate the time constraint. So there will be some priority. So let's do the coding, and in between, you are going to see how we deal with that. So first, I'm going to construct the graph. So here I'm going to write, so passing phase. So this is sort of long, right? Phase. So then what I'm going to do, and I'm going to build a graph using adjacent list. So here I'm going to use default dict, and I'm going to use a set to represent the neighbors, right? So for u, v, w in edges, right? So what we do is graph U. I'm going to, this is a set, right? So add a tuple that is V and W. It means that from U you want to arrive V. So this is the time taken. So then graph V. So we're going to add U, W. So we do this in a symmetrical fashion is due to the fact that it's a bidirectional roads or unidirectional road. You can, these two are almost equivalent. So once we have this, then I'm going to do the thing. So here, first I'm going to use a heap. So I'm going to use this like this mean fee costs, right? So I'm going to use this as float infinity times n. So this will be represents the absolute mean cost to reach a node I. So this is this list I'm called mean fee costs. Let's move a little bit slowly. So this is the mean cost to reach I, right? So this is the without any time constraint, right? So without any constraint. So we don't want to split that detail. So also we want to have another one at the mean. Let's also first initialize that costs. So at 0, so we should set it to be 0, right? Not zero, but the passing fee 0. Let me copy this part and put it here, right? So typically in a Dijkstra algorithm, so starting from the source, you are going to have 0, right? This distance is 0. So that's the one. And also I need to take care of the cost. So we have mean cost, mean fee cost. We have mean time costs. So I'm also going to set them to be float infinity times n. So then mean time costs at 0. So it's just 0, right? So this is let me also use mean time costs I is a mean of the lowest time pass to I already popped. So this will be our two distances, right? So when we do Dijkstra's, so we actually should take into consider both the two factors, time constraint and also phase. So then let's do also we need to initialize the priority queue or also heap. So here it's going to be something like this. So I'm going to passing phase 0. So this will be the cost, and then this is be the time, and then this will be the node. So let me fee time and node. So we put this fee in the first place for the first comparison key. If the fee is phase ties, so we're going to consider smaller time. So this is our order. So with that said, let me run the standard while loop, while priority queue, while heap. So first we get the fee, the time, and the node. So this heap queue, heap pop from this priority queue. So first we are going to do a check if node equals n-1. So in this case, we immediately return this fee. So this is very standard. So next if is very important. So if t is greater than mean time costs node, and at the same time fee is also greater than mean fee costs, right, node. So this I will not check, because if I took this node, and not only the t is larger, but also I should pay more fees for passing. So this is not a good pass. So if you consider the complement, it's either the t is less than or equal to this one, or the fee is less than or equal than this one. This would be good to consider, right? So first we consider the neighbors now. So for neighbor and time in graph node, So notice that graph node here in this problem, we set it as a set, right? So then the t via this node is nothing but t plus temp, right? So this time t via node is we arrive at neighbor via node, right? So now let's look at the relaxation part. If t via node is greater than max temp, auto temp, so this we don't need to check anymore, right? So now if it's not, as t is within the max temp limit, then we consider the phase. So phi via node equals phi plus passing phase at the neighbor, right? Then will be a relaxation, but it's a little bit more than the standard relaxation with one pure distance. So here what we want to check is we first check the phi. If phi is phi via the current node to arrive at the neighbor is less than mean phi, let's say mean phi costs neighbor. So if this is the case, or we can use less cost, that would be good. So we have mean phi costs a neighbor to be the phi via node. That's good one, right? So in this case, also we do heap operations, heap push. So we push to the priority queue or heap, and then what we want to push is the phi via node under the temp, right? The t via, so t via node, and also the node. The node will be the neighbor now, right? So that's the one. Otherwise, so if t, so that means that phi is larger than or equal to this one. But but in this case, we still need to consider, because if time is, if you do this one later, it can lead to no path, right? So we need to consider if t via node less than mean temp costs the neighbor, right? So in this case, so we're going to set the mean, so temp costs neighbor is t via node. So this is the best, right? If we have a valid path after this. If not, so we consider a suboptimal one. Oh, okay. So though the phi is not that small, but temp is smaller, right? So still have a possibility that we have less temp, but it might lead to valid path. That's the consideration. So this is again another relaxation. So first is relaxation on phi. So this is the put in higher priority than relaxation on time, right? That's our order. So then we do heap operation, heap queue, heap push to this heap. So let's see, the phi via node. So this might be larger, but you know, t via node smaller, right? So this will be the full code. So if after this while loop nothing returned, so we're going to return -1 according to the problem requirement. If you arrive at this return, meaning that we have no valid path with the temp constraint. So that's basically the full code logic. So let me first run it to see if it works. Yeah, it passes the 3 test cases. So now let's look at the generic case. Yeah, it passes all the cases and reasonably fast. So now let me give you a quick summary. First, this problem is marked hard by leetcode. However, from the algorithm side, it's rather straightforward, rather classic, I would say, the Dijkstra algorithm. But different from the typical Dijkstra algorithm application, here we have 2 things or 2 distances we need to relax, to do relaxation, right? One is phi and the other is temp. And in our code, the structure is like this. First, we construct the graph. Let me write some annotations. Preparation, construct graph. Secondly, so also preparation. So for running Dijkstra's algorithm. So this is up to here, right? And then this part, so the Dijkstra's algorithm. But the difference is that here we have two relaxations with phi as the first priority, right? And time second. So that will be the full code structure. So typically, if you know the structure, right, construct graph, this is rather straightforward. Make this preparation and know what you should hold in the heap. That will be half success. And then if you can arrive here, if and else if, right, these two relaxations, and then the code will rather straightforward to interpret. So this is maybe regarded as the first comment. The second comment is that actually if it's the first time you do Dijkstra's algorithm, or it's the first time that you use Dijkstra algorithm but with two distances, it's best to to run it manually to see the final details. So this is the second comment. The third comment, it might be regarded as an advertisement. So we have a YouTube channel which contains more than 1,000 carefully and rigorous YouTube videos distributed in more than 20 playlists. You're welcome to check out those free playlists to do some practices. I guess it might be helpful. With that said, I guess that's it for the current video. Thank you for watching.